Hello and welcome to the next part of calculus, differential equations. Now, there are three types of differential equations we'll be learning: the variable separable, homogeneous, and by integrating factor. Now, before we start, what is a differential equation? A differential equation is an equation with y, x, and dy over dx. So if we look at these example questions, these all have dy over dx, x, and y all together. Now let's look at the different methods to solve differential equations. The first one is to solve variable separable differential equations. This means that the variables can be separated from each other. Usually, it will be in this form: dy over dx equals to fx times g of y. So if you look at this question, they ask us to solve for y given that 1 plus x squared times dy over dx equals to 1 plus y squared. In this case, we can see that this and this are two separate functions. If I bring the 1 plus x squared over, I can show that this is in the form of a variable separable differential equation. I'm going to zoom in a bit. So how do we actually solve for y? What we want to do is bring all the y's and the dy to one side and all the x's and the dx to another side. So I'm going to bring the 1 plus y squared over. I'll just divide it. And if you see over here, I'm bringing the dx to the other side by kind of multiplying the dx to the other side. And then I have 1 over 1 plus x squared. So that's what it means by variable separable. I'm isolating the two variables. And I put the integral sign on both of them. And you can see, this just becomes two integrals. So we know that this is the integral of arctangent. So this arctangent y equals to arctangent x. And we only need to put our plus c once. Y equals the tangent of arctangent x plus c. Hopefully you can spot what is happening here. We are moving the y's and dy's to one side and x's and dx to one side. And then after that, we are integrating both sides. Our next type of differential equation is the homogeneous differential equation. So this is when dy over dx is in some function of y over x. That means there are a lot of y over x's in your homogeneous differential equation. Alright, so let's try this question. What are we going to do? The first thing I'm going to do here is simplify the right hand side. This becomes 1 plus 2 y over x. And we can see this is a function in terms of y over x. For homogeneous differential equations, I want to take y equals to v times x. And v over here just represents a function of x. And then we'll take dy over dx. If we differentiate on both sides, we're doing implicit differentiation. This becomes v plus x dv over dx. Now this is our substitution over here. We're just going to substitute this back into our differential equation. So we have dy over dx equals to v plus x dv over dx. And this is equals to 1 plus 2v. Y over x is just v. And after I simplify this, can you see that this just becomes a variable separable differential equation just in terms of v and x? So if we bring the v terms over to one side, as we did earlier, and bring the x terms to one side, we bring the dx over here, and we have 1 over x. Then we put the integral sign for both. We can see that ln, remember your modular sign, mod of 1 plus v will be equals to ln mod x plus c. Actually, we can change this c to ln of c. Because again, c is just a constant. It can be anything. Ln c is also just a constant. So we can have ln mod of cx, because if you remember your log rules, ln x plus ln c would just be ln cx. So we get 1 plus v equals to cx, and v is just cx minus 1. But we're not done yet. We need to find this in terms of y. We need to find what y is. And since v over here is y over x, we get that y over x equals to cx minus 1. So y is just cx squared minus x. Hopefully you can spot what is happening here. For homogeneous differential equations, we are finding things in terms of y over x, so that after we do our substitution, y equals to vx. make sure to differentiate also, so you can replace the dy over dx away, you will eventually manage to get a variable separable differential equation in terms of v and x. And then after that, you can solve for v in terms of x and then find y in terms of x. Now our last one is called the integrating factor. If we have this specific form, dy over dx plus px times y equals to qx, we can use this thing called an integrating factor to help us solve the equation. Now I know this is a lot of new content over here, but please bear with me. Let's try this question. Solve for the specific solution to the differential equation given that cosine x dy over dx minus 2y sine x equals to 3, and that y0 equals to 1. Now y0 equals to 1 just means that when x equals to 0, y equals to 1, similar to functional notation. Now if we divide by cosine x entirely, this becomes dy over dx minus 2y tangent of x. Remember, sine x over cosine x is tangent x. And then we have 3 over cosine x, which is just 3 secant x. And if you see, this matches our form to use an integrating factor. Now if you look over here, we have the y over here, the dy over dx. And then we have px, which is just negative 2 tangent x. And finally the qx, this function of x, 3 secant x. Now what are we going to do to solve this? As the name suggests, we need to use an integrating factor. Now I'm going to write down our px because this is useful. Our px is negative 2 tangent x. Our integrating factor, I'll write it as if, is just e to the power of the integral of px dx. This integrating factor formula is in your formula booklet, but more importantly is how you use it. So we're taking e to the power of the integral of negative 2 tangent x with respect to x. Now I want you to remember, how do you integrate tangent x? Now if you remember from an earlier video, the integral of tangent x is just equals to the integral of sine x over cosine x. And the reason why I want to do this is so that I can take u equals to cosine x such that du equals to negative sine x. And hence, this integral just becomes 1 over u du with a negative sign in front, which becomes negative ln mod u, or negative ln mod cosine x. And as such, this thing over here just becomes e to the power of 2 ln mod cosine x. We don't need the plus c because the plus c will just combine with another plus c later on. We just write the plus c in the final answer. Now again, if you remember our log rules, ln of a squared equals to 2 ln a. So this just becomes e to the power of ln mod cosine x squared. Anything square is just positive, so we don't really need a modular sign there anymore. Now there's one more thing I need you to remember. E to the power of ln x will be equals to x. So e to the power of ln cosine x squared is just cosine x squared, or just cosine square x. Wow, so nice, our integrating factor just reduces to that. So what do we do with our integrating factor? We just multiply the integrating factor throughout. So this becomes cosine square x dy over dx minus 2y tangent x times cosine square x equals to 3 secant x times cosine square x. And remember, secant x is 1 over cosine x. So this just simplifies to 3 cosine x. Now what I'm going to do, maybe you have guessed, is I'm going to integrate both sides. Wow, how do we integrate this entire thing? This looks a little bit scary. Now, fear not, there's a little cool trick. This left side just becomes, now fear not, I'm going to show you a little cool trick. This entire integral just becomes the integrating factor times y. This works for anything. So over here, our integrating factor is cosine square x, and then we have times y. And that's the magic of the integrating factor. If we use the product rule on this to differentiate, we'll actually just get this. And now let's integrate the right side. This just becomes 3 sine x plus c. Now we add a plus c because we are near the end. So let me just express y in terms of x. If I divide cosine square x over, this is like multiplying secant square x. So I have 3 sine x secant square x plus c secant square x. And this question asks us to find the specific solution when y0 equals to 1. So we write when x equals to 0, y equals to 1, and we solve for c. If we substitute all our values of x and y correctly, we should get c equals to 1. And this just gives us a final answer of y equals to secant square x times 3 sine x plus 1. Now to recap integrating factor, we want the differential equation to be in this form over here. dy over dx plus px times y equals to qx, where px and qx are functions in terms of x. Now if we manage to find this, the px is very important because the integrating factor is e to the power of the integral of px. After this, we'll multiply the integrating factor up there, and what we get is this very long thing which we integrate both sides. And again, this left hand side just becomes the integrating factor times y. And we'll integrate the right side normally. Then we can find y in terms of x. Depending on the question may ask you to find the specific solution to the differential equation, which we need to look at the conditions. And in this case, we find when x equals to 0, y equals to 1, and we find out what c is. And then we substitute this value of c into y so that we can find the specific solution. Now here's a summary sheet for differential equations. I know it was a lot to take in today, but thank you so much for watching. Hopefully with more practice, differential equations can become easier and easier to do.